So I can already invite the speaker. Niccolò Giaccasio will go through the ALICE highlights for us. So you have 15 minutes.
Thank you.
And we'll go with questions after that. Thank you.
So thank you so much. It is an honor to be here, showing you the highlights of the ALICE collaboration that we contributed to this conference. Let me start by essentially showing you the integrated luminosity of published papers that we have in ALICE, and we hit the 450 mark in the previous weeks. And we contributed to this conference with 42 parallel talks and 12 posters. This is the summary of this. To give you a bit of context, before starting the ALICE experiment, focus is to study the QCD in its extreme conditions, and we do this by using heavy ions that collide at ultra-relativistic energies. This is enough to produce the so-called quark-gluon plasma, the confined state of matter where the degrees of freedom are the quarks and gluons. The evolution of the fireball, so-called, then cools down, going through the phases of the hadronization and the freeze-out, and this is what we measure in the end, particles, hadrons, coming from the QGP. From the final state, it is interesting that we can go back. We can go back from the final state and infer information on the QGP. For instance, what we can learn, what we did already, is to measure the temperature, both kinetic, at the kinetic freeze-out and the chemical freeze-out. However, ALICE is not focusing only on the LED physics, but is also a rich program with the PP data, where it exploits all the PP collisions that we can get. For this, we upgraded our detector for the run 3 during the LS2. We replaced the inner tracking system with 7 layers of pixel detectors. The time projection chamber was upgraded with the jam readout to allow us to go to higher interaction rate. New detectors were installed in the forward region, both for muons and for triggering, and then this was coupled with an extensive update of the way that we process the data to allow us to digest all the wealth of data that we record more. And indeed, it's a lot more because the data taking rate in PP collisions is a factor 1,000 with respect to the run 2. And this is what we will be seeing during this talk. And then for the LED, instead, we have a factor 50 with respect to what we managed to do in the run 2. This is the snapshot of the current data that we recorded so far. On the left, you have this time the true integrated luminosity in the run 3 for LED collisions. This is about a factor 50 with respect to what we got in run 2 and run 1. Instead, in the right, you see here the integrated luminosities that we collected since the beginning of the run 3 with PP collisions. And already you can see, first of all, that the operation efficiency of ALICE is large, about 95%. And then with the current data, we already collected a factor 1,000, what the statistics that we collected during the run 2. This is not only coupled by large statistics, but of course, we need also good performance. And here you see just a few proof that the performance of the data is well enough for the analysis. And for instance, going from the cascades reconstructed in the LED, you see here the calorimetry with the pi0 reconstruction, the heavy flavor channels with the D meson, and then also in the forward, the prompt and non-prompt JPSI. Already with the statistics that we collected during the 2022 data campaign, we were able to beat our previous publication uncertainties by improving by a factor 10 with respect to what we measured in the, for instance, omega channel. Let's now get to the results. Here you see, for instance, one of the heavy ion collisions that we recorded. This is an event display. And one of the most basic measurements that we can provide is count how many tracks are produced in a heavy ion collision. This is what we did. As a function of the pseudo-rapidity, you see here the number of charged particles produced for different centrality classes. Here you see for the most central to the peripheral ones. And then it's nice to see that we're not far away from our expectations from what we knew already. This is, of course, nice as a confirmation. And the new points that we added with the run 3 collected data stays on top of the expectation. Then on the right, you see the distribution of the multiplicity distribution on the y-axis and compared as a function of the centrality. And here, again, we compare to the other experiments and previous previous publications, and again here we are consistent as a function of the centrality. This is all and well because it sets the stage for these basic measurements, and then we are allowed to go on. And we did this by, for instance, measuring the flow of nuclei. The flow, the anisotropic flow is indeed the one that is remnant when two collisions are grazing each other. And we measured with new statistics with the run3, the V2, the flow of the nuclei. Here you see on the left the helium-3, and this is allowing us to discriminate between different models of the way that these particles are produced. And then for the first time, we measured the flow of exotic particles, such as the hypertriton. This is for the first time that it was measured, and it nicely aligns with the results that we get for the helium-3. However, the statistical uncertainties are still large, and more data is coming, so this will shrink. We tracked down the onset of the collectivity with the small systems, and this you see reported again with the measurement of the V2 that allows us to quantify the flow that happens also in small systems. And on the left, you see what happens for the identified particles at low multiplicity, and on the right, you see what happens in high multiplicity. And there, we observed different behaviors at low multiplicity, where the mass ordering that we see at high multiplicity disappears, and also the quark content ordering disappears. So we tracked down the onset of the flow. Then, using the most central collisions, theory tells us that the fluctuations in the system then translates to fluctuations in the average momentum and multiplicity. This allows us to access somehow the speed of sound in the medium, in the QGP. However, this comes with a caveat, as theory also tells us that the measurement that one extracts from this data depends a lot on the estimator that is used for the centrality. And this is what we did extensively, where we measured with a plethora of estimators covering different multiplicity regions, covering both the multiplicity and the transverse energy, the so-called speed of sound. This is summarized in this plot over there, where you see as a function of the gap in eta, the speed of sound that is extracted, and here you see that as a function of the different estimator, there is a large difference between the two, essentially giving us more information on how to interpret the measurements that we do on the speed of sound. Then this is not all what we do for the heavy ion. We also measure the information on the temperature of the QGP with the measurement of the direct photons from the collision. Here you see an example where the comparison is undershoot, the measurement is overshooted by the theoretical predictions, and this needs to measure this also as a baseline in high multiplicity VP collisions to challenge the models. We measure also the decorrelation that comes from the presence of the QGP into the jets, where essentially the hard partons get deflected. And this you see here as a function of the opening angle of the jets, where in PP it is much more below with respect to red lead. And then using the most peripheral instead collisions, we're able to essentially look the behavior, how the nucleon interact with each other by using the so-called the UPC, ultra-peripheral events, and in particular the incoherent photoproduction of the J-psi. This is nice because a gamma of one nucleus interacts with a nucleon of the other nucleus. And indeed, if you measure the production, then we are able to see that the probe is looking at the subnucleonic degrees of freedom within the nucleus. Let's now move to the QCD part, focusing more on the P collisions. Let's now, starting from the measurement of the J-psi and the psi2s, for the first time we were able to measure at mid rapidity the J-psi production down to 0 momentum, and this we did in the channel of electrons. And if you compare this to the previous results that you see on the right with the muons, you see first of all that there is no strong dependence on rapidity, but then if you plug in the models, you have also predictive power, as you're able to discriminate between the way that hadronization happens after the interaction. Going on to a similar mass, but okay, Hypertriton and Exotica, we were able to measure the matter and antimatter hypernuclei. That is a nucleus when you replace a neutron with a lambda. And this allows us to do some spectroscopy into the hadrons, because the yields that we measure depend on the number of excited states. And indeed, this is telling us how many they are and how much they contribute to the final state. And this is we did for the first time for the LHC for the helium-4 lambda and hydrogen-4 lambda. Then in PP collisions with the RAN3 data, we were able to shrink the uncertainties that we measured for the Hypertriton channel, and then you see here, for instance, the ratio of the Hypertriton over lambda compared to the different model of particle prediction that involve or not the coalescence. Then moving to the heavy flavor sector, this we did again with the RAN3. We used the wealth of data that we collected during the PP data taking campaign, measuring the strange and non-strange mesons. You see here the signal extraction, and then comparing the two as a function of the momentum here by doing the ratio. This is still a challenge for models to reproduce, involving indeed the way that the hadronization happens. And then this is, again, another way to investigate the production of D mesons, using the correlation between the meson and the high PT hadrons. Then we see that in the near side, the strange and non-strange D mesons behave differently, constraining the way that again, the models do the hadronization. Moving from mesons to baryons, we measure for the first time the excited state of the sigma C. With a very elegant way, we provided the measurement of the ratio, and this is, again, based on consideration of the mass. They should be produced in equal number, but this is yet a challenge for models to describe. Lastly, in the strangeness sector, we measured the mass of the hyperons, improving on the measurements that were done in the 90s. We provide a 10-fold improvement in the precision of the omega mass measurement. This is important because it is an input for the lattice QCD calculations. And not only that, but checking the difference in mass, then we verified the CPT conservation in the strangeness sector. Okay, this is the past, because we did it already, or is being done, but ALICE has an important future that is already planned, and you see ahead that it covers the next 20 years at least. The two upgrades that will happen during the next long shutdown will be the installation of the focal and the ITS-3. The focal will be covering the forward rapidity gap with a calorimeter focusing on the measurement of low X gluon density and the isolated photons and pi zeros. And this is already in the construction, when instead the innermost layers of the ITS will be replaced with silicon-only ultra-thin technology, allowing us to improve the precision of the pointing resolution by a factor 2 to essentially drive the measurements of the dileptons and heavy flavors. This is not only, this is, well, the first step. The second step will be the LS4 upgrades that will be, that we see ALICE replaced by so-called ALICE-3. Carrying out the next breakthrough in heavy ion physics, improving both the precision on the pointing resolution on the x-axis and on the interaction rate that we will be able to collect. This is important because it will be the technology driving the future experiments at the FCC. And the observables that we plan to access will be the measurement of the temperature of the QGP, indeed, because this is limited if one does it with the hadrons to the temperature of the chemical freeze-out, when instead if one uses the dileptons measured in the continuum from the slope, one can access the temperature of the QGP. And the nice thing is that if one uses the momentum of the dilepton pairs, and one is able to essentially follow the temperature evolution of the QGP. The other important measurement is how a charm diffuses into the QGP, and this will be another highlight unique to the ALICE-3 detector because it needs extreme good purity and tracking down to very low PT. where the signal is the strongest. And here you see, for instance, the figure of merit comparing what we will be able to achieve with LIS3 compared to the old statistics that we will be getting with run 3 and run 4. The last thing will be, again, on the hadron physics, you see here how the thermal model, well, the model predicts the plethora of states coming out from the collision. This way we'll be able to test it using the technology that we developed for the run 3 and will be maximizing for the LIS3, essentially allowing us to rediscover what we call the strangeness enhancement, but in the charm sector. The R&D for the LIS3 detector is already in the way. I will flash just a few test beam and the development of the engineeristic models. And I come to my conclusion. I showed you that the QGP is our main topic. We try to learn as much as we can on it, but then we also have a strong QCD program that we will plan to develop with the future upgrades of the experiment. Thanks.
Thank you. Thank you. Okay, it's very nice overview and very interesting results. We'll take questions from the room now. So indeed, it's quite hard to see, so don't hesitate to stand up. Oh, there's one here.
Thank you for the nice talk. Can you go to slide 4?
Too many slides. 4.
Right. So my question is here, I think this is your paper, and my question is how you really determine this crossover time and now this kinematic freeze out time. So this is depends on model, right? So how you really determine?
It depends on, sorry?
No, I mean, in principle, so those temperature shows up at a really early time. So you cannot really measure directly, right? So then how you can extract those temperature from data?
Okay, no, indeed. So this is also, let's say, consistent in a framework, in the sense that we, from the final state, from the abundances of the hadrons, how many pions, how many kaons, how many nuclei, how many strange hadrons, then we infer information on when the abundances of such hadrons were fixed, which is the point at which the hadronization happens. And then, for all concerns, the chemical freeze out, the temperature comes from the spectral shape. That is how hard or how soft the spectrum is. And then this is, in a consistent picture, then the mass is the only driving parameter here. And if the temperature is common, then pions, protons, kaons should have the same the same temperature. And this is indeed what we find. And but okay, this is let's say indirect measurements with the application of some models.
Okay, thanks.
Thank you. Any other questions? Yeah, right here in the middle.
Hi, thanks. Thanks for the nice talk. On page 31.
Too many slides. Yes.
Yeah, just in the lower right plot, I'm just having a little trouble understanding the improvement here. It looks like the uncertainty bars are a lot bigger. So how do I read this? What's the blue compared to the red?
So you should read in the sense that in the run 3 and 4, the measurement will be so challenging that it will be essentially not conclusive. So the ALICE3 will be really the only way to measure the. So this will be ALICE at the end of run 3 and 4, essentially where we will be only able to have the first look, and then the question will be resolved with the ALICE3.
So okay, so the prediction is sort of the red?
Yes.
Okay, I see. Okay, thank you.
Okay, thank you. I think we have to move on, so thank you again.
Okay, and our next speaker is Yasmin Amis, and she will talk about LHCb highlights.
Thank you very much. Hello, everyone. It's an absolute joy to be here today, standing in front of this beautiful audience that I luckily cannot see very well. And I'm more than happy to show you highlights from the LHCb experiment. So LHCb, in a nutshell, it was originally designed to really study CP violation and rare decays in the beauty and charm sector. However, you will see throughout this talk that one of the beauties of LHCb is that we've done a lot more than what we were originally designed to do. My colleague and friend Monica, I told you how important it is to be able to cover the forward region, and this is indeed the architecture of our detector, which is along the beam pipe, and you can see we have this forward architecture that I will tell you a bit more afterwards. So during the first 2 runs of the LHC, we have collected a good amount of data about non-inverse femtobarn of proton-proton collisions, but also the program expanded to be able to collect also lead data, lead-lead data, P-lead data, and also we have opened a new era, which is around the fixed target experiments. The reason why we're able to do all of this is because we have an excellent vertexing system, tracking system, and particle identification, and that the extension of the program was also possible thanks to the versatile trigger system. Now, a few words about the collaboration itself. As I told you, originally we were meant to study CP violation rare decays. As then the years went by, we have extended this to semi-leptonic decay, rare decays, electroweak. I'll give you an example today, and as I said earlier, heavy ion and fixed target. So we are a small but mighty collaboration. So for ICHEP, we have about 30 new results. I made the choice of selecting just a few to walk you through today. And here you have a feeling of how we have expanded with a number of papers and institutes and members joining our collaboration. So far at the LHC, we have discovered one fundamental particle, as we all know which one. And since then, there was nothing much. On the side of QCD, however, if you think about it, I took this picture from a screenshot from Wikipedia, you can see that now we have impacted also kind of our greater knowledge of QCD and what we know about the constituent of matter, as indeed we have discovered 75 hadrons at the LHC, which is quite impressive. So it is quite a privilege for us to be able to contribute to this sort of textbook physics and to have this as a heritage. So I'll show you a few examples, and one which is kind of a classic spectroscopy example. We also have exotic results which were presented in parallel session, and invite you to have a look at those. But today I'll focus on a very beautiful example of how you can do QCD with kind of the classic knowledge that you can have. So this is the study of what we call a muon Dalitz decay of the Chi-Bs. So the way it works is very simple. You have your upsilons over there, which are beautifully reconstructed and separated, which decays into a pair of muons. Then to these, you will add another pair of muons, and then you can see here you have the spectra over there. So then, because you have 4 muons in the final state, what's really nice is that then you're able to separate and see new states, and this is what we're reporting here for this result, where we're seeing for the first time the muon Dalitz decay of the upsilon going to a pair of muons. So with this analysis, we're able to report the masses and the mass differences. Of course, when we look at the mass differences, we factorize out a lot of the systematic uncertainties, and this is why the results are more precise. Anything we can learn about this region of the phase space is also useful for what we can do in other regions of the phase space and how we can probe electroweak physics. So this, my colleagues from ATLAS and CMS told you already that it is really beautiful to be able to probe as well as we can the electroweak part of the standard model. And this is what we do here with the effective leptonic weak angle decay. So the way that it works, this was explained a few times, is that one measures the forward-backward asymmetry, and then with this asymmetry, then when you plug in your favorite generator-level models, you can then trace back this to the observable that you care about. So this is exactly what is done here, and this is done in the forward region that we can explore at LHCb. So what we do is that this forward-backward asymmetry, which you get from the little sketch that I showed you up there, you do this in bins of eta, and then this is interpolated across these bins, and you can try the various configurations of the fit that then give you the knowledge that you have about the angle that you measure afterwards. So for this measurement, you have a combination of the results, which we are showing here, which you can see is fairly competitive with the experiments which are more dedicated for this type of physics. And then we have the uncertainties that, as usual, come from the knowledge of the statistical sample that you have, your systematic, and then the PDF. So we have this beautiful result that we're really happy with. Now, let's change a little bit gears and explore another sector, another way of doing flavor physics. And here what we're interested to do is to try to search for new physics in an indirect way. So the way that we can do this is to explore B2SLN transitions. So these are flavor changing neutral currents. You have here an example of a Feynman diagram which shows you how this works. And then if you discuss with your colleagues from theory, they will always tell you that what's complicated about this kind of decays is that you have a multi-scale energy problem, in the sense that the energy that you're trying to probe, depending on whatever is your favorite leptoquark that you're trying to test, this will be typically at high energy, so TeV scale. But then, because you're using B mesons, so then you're going to be quote-unquote polluted, but all the knowledge that you have to somehow gauge from the gluons that you have all around that, and you cannot get rid of. So a framework which is very convenient to doing all of this physics, which we call AFT, the way that you do it here is that you can factorize out the high energy scale, and then you try to see what kind of you can do with the data that you have. So typically what you have to remember is that you can never fit everything at once. So if you look at the expression of the effective Hamiltonian over there, you will see that you have expression that will come from the CKM matrix, and this you trust your colleagues who are studying everything about the CKM matrix, which will give you this as an input. So what you have to remember from this sketch over here is that if you look at the Q-square distribution, which is the invariant mass of your dilepton in the final state, if the kind of physics that you care about is this one, you have a very rich phenomenology. What it means is that here you will have what we call the photon pole. It's called photon pole, as the name suggests, because it's very close to zero, and these Feynman diagrams will be dominated by the photon. Then you continue, and in this region here is where you have the interesting stuff. But the interesting stuff, I mean, is where you have things which are very sensitive to your short interaction. And then you'll continue and you'll have your good old GIPSI, the Psi2S, and then you have also an interesting region over here. So then, how do you do this? Well, you have a few ways of studying this. Either you fear nothing, and you try to fit as much as you can, including everything in the spectrum over here. So this is what was done in this paper here, which is referenced, where we studied both the local and the non-local effects. And this was presenting at length at Morion QCD. The other options that you have is to try to cancel out as much as you can everything that you cannot really control from the QCD. So for that, you enter the family of lepton universality test. We love them a lot because everything that has to do with the knowledge that you don't necessarily have from your operators and everything that has to do with the long distance cancels out. Of course, they come with their bit of complications, which is that you have to study electrons, which can be quite difficult in this environment. And here you have an example of the result that was presented about a year and a half ago. So now let me focus on a new result that we have for ICHEP, and that is the angular analysis of K star EE. So here you try to do a little bit of both things that I told you earlier, which is that you're going to try to measure the angles, and then you're also going to do that with electrons to then see later on what happens when you compare that in the muons when you try to cancel things out. So here you have an example of one of the analyses that we do in LHCb. So you have 4 dimensions that you will use to be able to access the angular observable. So the first thing you do is you fit the mass, obviously to be able to separate the signal from the background, and then you will fit for the 3 angles. So from the 3 angles, I will grant you that it's not straightforward to see how you go back to the Wilson coefficients, but you can read the paper or trust me when I tell you that from the angles, you can then go back to the amplitudes and so on and so forth, and then be able to say something about what happens to the new physics or not. So here you have an example of the the projections in the angles in the helicity frame, and then you see that you're able to separate all the different components. Now, in this kind of field, people are familiar with the different bases that one can use to extract the information, and in this particular example, we're using this basis here with the p parameters that we're measuring here in the electrons in this region, which we call the central one. Let me go back here 1 second. The central one here refers to this region for the first time. So you have here all of the observables, and these are all best measurements. Up till now, the competition that we had naturally came from the B factories, which are very good to be able to study electrons. And then what we do is that we compare this angular observables with what we have with the muons, and this is what we call now the Q variables. So the overall message is to see that these are in quite agreement in the sense of lepton flavor violating effect. They seem not to be observed over here. So I told you that LHCb likes to kind of reinvent itself and then have new ideas around. So a few years ago, some of our colleagues figured out that if they combine the information of the detector in the way that was not particularly intended for that purpose, they see that they can isolate helium, which is quite cool if you think about it, because then you can make connections with experiments which are in outer space. So we had this result a year ago where we measured the helium, and then what we do to convince ourselves is that it is a helium is that you combine it with a pion, and then you have this thing which we call a hypertriton. So we have this beautiful, extremely clean observation of a hypertritons at LHCb, and this was one of the highlight results that we had a year ago. Now let's continue now that we have this knowledge. What can we do? So what's interesting is that this anti-helium, we can have them in the universe as part of some of the antimatter annihilations that we can have. And there are various scenarios that can say we expect this number of anti-helium to be produced, for instance, in lambda B decays. So now that we have access to this knowledge, and you remember LHCb, the B stands for B decays, and we have also one of the beauties of working in a hadronic environment is that you can produce also a lot of lambda B decays. So what you do is that you search for the signatures that you have over here. You use what you know very well, which is this decay as a normalization, and then you do a search. So no signals are found here in the different topologies that we have explored. So here you can have a look at either the fully exclusive decay, or then you can add X's for the numbers of particles that you're not reconstructing, and then you can have here an extrapolation for a almost fully inclusive decay. So for this is the first result that we have of anti-helium production in anti-lambda B decay, and for this we're looking forward of the impact of the result in the theory community, which has to do with dark matter searches. Now, let me mention the upgrades of LHCb. So as you know, we have gone through a major upgrade. In fact, all of our tracking system has been replaced. The particle identification systems have been upgraded, and we have redone all of the readout of the detector. Let me show you some highlights of how the detector is performing so far. So here you have some images that show you how the tracking and the particle ID are doing. So something which is quite interesting for us is that we can see, for instance, if let's take, for example, what goes on with the IP resolution, or here with the hadron identification, is that even though we are now in a harsher environment that we need to have a higher pileup to be able to collect more data, we see that the performances are showing that we're quite there, which is very encouraging. Another way of looking at it is the following, is that as part of this upgrade system, we have also removed the first level 0 hardware trigger, which was really a limiting factor when it comes to understanding, to be able, to study hadron decays. So this has been removed, and now we have a fully software-based trigger system which uses both HLT1 GPUs and then also CPUs at HLT2. Now, all of this reconstruction is done online, and one of the beautiful ways of seeing the impact of the removal of this first level of trigger is looking, for instance, at this plot, which really speaks for itself. Because you can see here the variations of the efficiency. For instance, here is a B hadron, and you look at it in PT, and you can see here the gain that you have, which is really beautiful, and it was one of the main reasons for this upgrade. So I'm not sure why this looks broken, but I will change it afterwards. All right. Now that we have all of this, we're thinking also about another upgrade, which we will have in our bit further future. The reason for that is that even with the first LHCb upgrade, when we look at the projections of what we expect in terms of statistical uncertainties of all the observables that we care about, we will see that they're all statistically limited. So there is still room to kind of improve our knowledge of flavor physics and all of the other physics that we can do at LHCb. So for this, I give you here some example of some of the projections of what you can have in terms of the measurements of the phases in both of the BSAP-S or in the CHARMM system, and also what we can get if we were to improve our knowledge of the photon polarization, for instance. So there was a framework TDR which was approved a year ago, and this work is actively ongoing. So to conclude, so in the last years, we have wrapped up a number of Run 1, Run 2 legacy results. We're extremely proud to have those now. Our program, as I showed you, is in constant evolution, and this is one of the beauties of the detector. The Run 3 upgraded detector is running stably. We're expecting improvements in the months to come, and we have demonstrated that we have the trigger efficiency, which are improved for the hadronic channels, and we are actively preparing upgrade 2. Thank you.
Okay, thank you very much for this very clear and engaging talk and the impressive new results. Thank you. Are there questions?
Hi, hello. I have a question. Very nice talk. Could you go into a bit more detail about the Science-Crafted-Weinberg measurement, which is a very nice measurement?
Yes.
Could you maybe detail a bit more how you managed to greatly improve your systematics and also your theory uncertainty? I assume especially PDF uncertainties. So
sorry. You mean this one?
The science, yes.
Yes.
So it seems the systematics and the theory have greatly improved, and I assume also the PDF uncertainties. So can you sketch how you managed to reduce these uncertainties?
So here what is done for the PDF uncertainties is that we have 3 sets which are used, and then they're used in arithmetic knowledge. And then they're all treated together. So that's the main answer, I would say, to your question.
Okay. And for the systematics?
And for the systematics, so for the systematics, what we have now is that the level of background is extremely small. So that's one thing. So you have 2 sources of background, one that comes from Z to tau tau, and the other one that comes from heavy flavor in general. So this you can reduce very nicely thanks to the IP resolution. And then the other important thing is that everything that has to do with alignment. So this measurement uses a method which is called the pseudomass that allows you to control really well everything that has to do with the momentum scale. So we have a dedicated paper for that. And for that, you are able to have a very nice control of your systematics.
Okay, thank you.
Okay, thank you. Are there more questions? I can see one over there.
Hi, thank you very much for the nice talk. About the measurement on slide 10, where you have now essentially taken a look at the production of the antihelium from the lambda sub B decays. Will you also try to convert this in a flux that should be seen, for example, by AMS too, or what are the plans for those results?
I'm not sure if this is something which we can do, is the honest answer. Something that can be done here is that one of the things that we would like to improve is to make sure that everything that has to do with deuterons and all kind of other possible contamination, that these are kind of well set. But then, as far as I know, we will see, once we'll have kind of feedback from the theory community, if there are more models that can be excluded, things like that. But as far as I know, I don't know if this can be kind of converted to a flux. This I don't know.
Okay, thank you.
But there is Dan, one of the main proponents there, so he can answer.
Hi, just to rescue Yasmin for a bit. So in principle, it could be done, but not by LHCb by itself. One could, in principle, take these branching fraction results and convert them to a flux results. But for that, you need to take into account effects such as the distribution of dark matter, the effect of the magnetic field in the solar system, so essentially you need external input to do that. We are happy to do it and collaborate with interested parties. However, like I said, it's not something that we can do just on what you see on the plot. We can make statements on the branching fractions, on the upper limits, and this is what we do in this conf node.
Okay. Thanks a lot.
Thank you very much for this clarification. Any more questions? I don't see any, so let's thank her again.
Thank you.
Thank you. It is now a pleasure to invite Jim Libby, who will tell us a little bit about E plus E minus B factory results and highlights.
All right. So, good morning, everyone. I'll be presenting the E plus E minus B factory highlights. So, as we're moving away from the LHC, I should set the scene for what we're talking about. This is intensity frontier physics, where we hope to make precision measurements using large samples of B mesons. And also we will search for rare and forbidden decays. So essentially these are indirect searches for beyond the standard model physics, and key to the whole enterprise is very high luminosity. Should also point out that much of our program is complementary to that of LHCb and the Hadron machines that you've just heard about from Yasmin and others. So the outline of my talk is in 3 parts. I'll begin by just discussing why we do this physics at the Upsilon 4s in E plus E minus collisions, and then I'll talk about measurements of the Cabibbo-Kobayashi-Maskawa matrix. Then I'll mention some results related to the so-called B anomalies in the second part of the talk, before moving away from the B program, talking about what we can do in other areas of physics, and also talk about the future of Belle 2. And so some of you may have realized the titles of my sections have taken inspiration from one of the most famous people from Prague, Franz Kafka, whose death centenary is being commemorated this year. So, to the castle. This is a tale of Kay's relentless, unavailing struggle with an inscrutable authority in order to gain access to the castle. So we can paraphrase this to think about our quest to get beyond the standard model and find that beyond the standard model physics. In terms of the B sector, the main tool we have is a so-called unitarity triangle, which relates together the elements of the CKM matrix, those that are measured in B transitions, to the CP violation in the standard model. So the area of this triangle is related directly to that, and we can make many measurements around this triangle. So to begin, I'll just explain the environment in which we work. So at the Upsilon 4s, just above threshold for open B meson production, our cross-section is roughly, the hadronic cross-section for BB bar is roughly 1/4 of that to other hadronic final states. So we have good signal to background. Because it's E plus E minus, we have constrained kinematics, and we also have no other particles produced. There's no fragmentation particles. We just have the 2B mesons. Therefore, we have excellent neutral and full momentum reconstruction for missing energy. And we can even go as far as reconstructing the whole event and do something called hadronic B-tagging, which I'll mention later. Now, the asymmetry is there so that we can make time-dependent CP violation measurements by boosting our Bs in the laboratory frame. So we need to have information from both Bs to do the B-tagging, to understand their flavor, and we benefit from the coherent evolution that takes place from 2B mesons produced at the Upsilon 4s. So we get very high tagging efficiencies at Belle 2, and we have macroscopic measured distances before the Bs decay. So the main results I'll show come from 3 experiments. The first generation of B factories, Babar and Belle, that started around 25 years ago. And now we have a second generation experiment, Belle 2, which began in 2019. They've all collected data sets of approximately half an inverse autobahn of data, and I'll show results from this as we go through. So to the CKM matrix and the unitarity triangle. So these 3 pictures show the evolution of how well we have now learnt the apex of this unitarity triangle. From the first generation of B factories, this was the principal result, that this was pinned down. And then today, with further information from LHCb and theory, we know it very, very precisely. So you may ask yourself if this is still interesting or not. It is, because there are only 2 standard model parameters defining where this apex is. So we can actually make many, many measurements in different processes, some of which are sensitive to new physics and others that are less so. And if you find tensions here, this can be an indication of new physics. So 2 examples I'm going to show. The first is a long-standing issue with the measurement of VCB, the magnitude of VCB, which comes in the transition of a B quark to a charm quark in semi-leptonic decays. So there are 2 ways of measuring this, where you do different things with the hadronic final state, whether you care what it's gone to or not. So if you don't care, it's measured inclusively, and if you look for a specific charm meson, such as a D or a D star, it's exclusively reconstructed. And what you see is that the measurements here of both VCB and VUB are in tension with one another, and this has been long-standing between the exclusive and the inclusive. So recently, using the legacy datasets, Bell and Babar have both produced new measurements of VCB, where for the first time they've used the full angular distributions in B to D L nu and B to D star L nu, and this seems to boost the value of VCB away from earlier measurements. And it seems that this might be an approach where we're actually learning more about the form factors by doing this angular analysis that will ease this tension in the long term. The second measurement is related to the angle that sits beneath the apex of the triangle, alpha, or phi 2. So this is the least precisely known angle of the unitarity triangle. And to gain access to it, you must actually measure all the final states with 2 pions, or 2 rows, in the final state from B mesons, both charged and neutral. And you measure CP asymmetries and branching fractions. And then you can combine all of these together, and you get a measurement of alpha. And the least well-known part of this is the B0 to pi 0, pi 0, which is very well suited to the E plus E minus B factories. So we have a new measurement from Bell 2, which measures the B0 to pi 0 branching fraction, and then using tagging information as well, we can measure the CP asymmetry. So even though we have slightly less data than the first generation B factories, these measurements are as precise and will go into improving the value of alpha. So I move to the second part of the talk. So the trial, in this novel, Joseph K. is persecuted in some way by an inaccessible authority for a crime that he nor the reader never fully understands. So this can be an allegory for dealing with funding agencies and university administrations, or in this talk, I will give it as an allegory of B anomalies. And of course, as many of you may know, the penguin plays a very important role in these. So there are 2 types of B anomalies. The first is in flavor-changing neutral currents, where you have a B to SLL transition, and this only proceeds via a loop in the standard model. And so this is where the penguin appears. We also have a box diagram. There have been long-standing 2 or 3 standard deviation tensions between the measurements and the predictions. But in recent years, as shown by Yasmin, it's been realized that long-distance effects can contribute here, and this somewhat weakens the tensions. And the lepton universality violation that was there for some time was cancelled about 18 months ago. There's a second type of anomaly that happens in semi-tauonic decays. This is the B to C tau nu transitions, which then can be compared to the semi-leptonic decays to light leptons. And here, this has been measured in many experiments, and if you take the average and the very well-known theoretical prediction, you see there's a tension between them that is around the 3 standard deviation level. So Bell 2 contributed a new anomaly last year when we measured B to K nu bar for the first time. This is very theoretically clean because it doesn't suffer from these long-distance contributions, and is also sensitive to 3rd generation. How we managed to make this measurement was to use the topology of the events such that we could separate between the continuum background and other BB bar events by exploiting the fact that we have lots of missing energy when one B decays to K nu bar and the other decays inclusively. And we've got around 8% efficiency for this tagging method, which relies on machine learning. We then make a fit in the invariant mass of the 2 neutrinos and this classifier, and what we see is a signal across the whole range here at both Q-squared bins and across the classifier. And this gives us a branching fraction which is above 0 by 3.5 standard deviations, and is in tension with the standard model at around 2.7 sigma. So a new measurement for ICHEP is also third generation sensitive, where we have the B0 going to K star tau tau. This is interesting because it correlates to other anomalies. So this is the RD star. Blue is the K star tau tau cross-section, and it can be boosted by up to 3 orders of magnitude if you have an explanation for the RD star with new physics. So we use hadronic B tagging, where we fully reconstruct one hadronic B on one side, then we get the momentum of the other B, and then we look for the decay products of the K star and the tau, and then there's lots of missing energy from the neutrinos. Again, we rely a lot on multivariate analysis and using machine learning. Missing energy is important, and also the additional energy that's left in the calorimeter. If we've really seen anything, there should be nothing left. And this is fit to extract the yield. So there is no signal here. Everything you see is background. The signal would have been uniformly distributed. But it allows us to set the best limit so far on this process, which is starting to come down towards this interesting level, maybe predicted by models of new physics. And this is improved over the previous ones by our better understanding of tagging and greater signal efficiency. The final measurement on the B anomalies is our first measurement of RD star. This again is done with the hadronic tagging. We use leptonic tau decays, and we use both charge and neutral Bs. Key observable is that if you've reconstructed everything, you should have no extra energy in the calorimeter, and here in red is the signal. We also managed to extract from the whole fit, looking at other regions in the missing mass, the normalization, which is the semi-leptonic decays to light leptons, and we can measure this ratio. So our result is here. It's only done with roughly a quarter of the data that Bell had, and it's in agreement with both the theory and the previous measurements, but there's a huge amount of potential to help hopefully resolve or better understand this anomaly as we get more data. So the final part of this talk, this is one of the most startling openings to a story in literature, when Gregor Samsa wakes up and finds he's been turned into a fly. Now that has double meaning for Bell 2. First, we're more than a B factory, we do other things, and of course we must transition from being a first generation to a second generation B factory. So why we're much more than a B factory is if you look at the contributions to the cross-section at the upsilon 4s center of mass energy, you have equal amounts of charm and tau as well as BB bar. So we get the advantages of our excellent neutral reconstruction and missing energy to make measurements there as well. We also take data sets away from the upsilon 4s nearby, mainly for QCD studies and spectroscopy, and I'll highlight a result from the 1s and 2s samples collected by the Bell experiment. So in that data sample, where you have hadronic decays of the upsilon 1s and 2s, this is OSI suppressed and hence rich in gluons, and previously seen has been enhanced baryon production in the final state. So it begs the question of whether you can see pentaquarks or not. So looking at the J psi lambda inclusive spectrum from upsilon 1s and 2s decays, we then inquire about the invariant mass distribution of the J psi and the lambda, and we see here a peak which is consistent with the previously observed pentaquark candidate in the psi b decay, the PCS 4459. So this is the first exotic seen in upsilon 1s and 2s decay, and this shows the power that we have to understand spectroscopy also at Bell 2. So we also have many other results in low multiplicity physics. We have the world's best measurements of a fundamental parameter, the tau mass. We have a lepton flavor violating search, tau to 3 mu, and the best limit on that. We have contributions to the E plus E minus to hadronic cross-section that appear in the theoretical calculations of the hadronic vacuum polarization for G minus 2. And we also can do searches in the hundreds of MeV to GeV range for dark sector particles. Here is an example of a dark scalar going to 2 muons, which rules out part of the space allowed to explain the G minus 2 anomaly. So you'll hear much more about this in Iejima-san's talk on Wednesday, particularly related to the tau and G minus 2. So now, in my closing minute or so, I'll talk about the status of SuperKEK-B and Bell 2. So our run 1 took place between 2019 and 2022, and then we had a long shutdown. In that first run, we achieved a world record instantaneous luminosity of 4.7 times 10 to the 35 inverse centimeters squared per second. In this first shutdown, we installed a new 2-layer pixel detector, and there were also improvements to the accelerator, particularly to reduce machine backgrounds. So in run 2, which started earlier this year, we've got back to a luminosity close to our world record, and our PXD2 is working well. Here I show the impact parameter and where the first hit was, whether it was in the first layer, the second layer of the PXD, or with no hits in the PXD, and you see the improvement you would expect as a function of the momentum. However, of course, our goal is a long way from 4 times 10 to the 34 inverse centimeters squared per second. We want to be taking data above 10 to the 35. And run 2 has been challenging. We've had certain accelerator issues, particularly we've had things called sudden beam loss, which can give very large doses to our detector. And this has been hampering increasing our luminosity. 2 such losses led to us having to turn off our PXD because there was some damage, and as a precautionary measure, as we understand the machine better, it will remain off for a while. So we have not taken very much data yet in run 2. The whole idea is to improve the accelerator and reach these higher luminosities, and there's been significant progress in understanding some of these problems, and remediation will take place during the summer. Longer term, run 2 is long. We will go on until 2028 or 2029 and hopefully accumulate a few inverse attobans of data and reach an instantaneous luminosity somewhere between 1 and 2 times 10 to the 35 inverse centimeters squared per second. Then there's a plan for a longer term upgrade which will improve both the accelerator and the detector, with going on into the 2030s to accumulate tens of inverse Attoban size data set. And recently we have published a technical framework, CDR, which describes our upgrade plans. So I'm out of time, so I should conclude. So there's a rich history of E plus E minus at the Upsilon 4S, previously Bell and Babar, and now Bell 2. We have many papers on the archive or published, and also several preliminary results, 7 of which were shown for the first time at this conference. And our results are as good or better than those from the first generation due to improvements in our techniques and also in our detector. Of course, the intensity frontier is challenging, as I've just shown you. However, we have a plan and a roadmap to get to several inverse Atobans of data in the years ahead. So I leave you, if I can, with a quote from Kafka about how beauty is important and will keep us young, as I hope Bell 2 will remain as well. Okay, so thank you very much.
Thank you, Jim. Very nice talk. We have plenty of time for questions in the audience. Oh, right here at the front, middle. Oh, there's one there.
Okay, let me start. So thank you for a very nice presentation. You mentioned the most accurate the measurement of the tau lepton mass. So can you say a few more words about this measurement and what you can do in the future with further improvements on this important standard model parameter?
Sure. Let me go back, hopefully. There we go. So we use this pseudomass technique where this is in 3 pion, tau to 3 pions. And if you use this, this edge is used to determine the mass of the tau. So there are 2 things we need to know very well to be able to do this, one of which is our momentum scale, and the other is the beam energy. And that's what's allowed us to beat down this to 110 keV. So we have some ideas of how we can improve those 2 systematics going forward. The beam energy actually relies on accurately knowing the shape of the Upsilon 4S resonance, and that is something we're improving, because when you move away from the resonance, the effective beam energy changes. And with the momentum scale, we did this in functions of momentum and in terms of the angle, and we know that if we bin finer in this or use other variables, we can potentially improve the momentum scale measurement as well. But it's difficult work, as we're already systematically limited. So that's where we are with the tau mass.
Thank you. Another question?
Thank you for this nice Kafka quote. Indeed. I wanted to ask about something else. because Bell 1 measured, for instance, photon-photon transition form factors.
Okay.
And now you have much, and there are many not concluded cases. And in addition, we measure now many exotic resonances that we don't quite understand them. And my feeling is that this measurement, that the repetition of this program would be very useful for Bell 2 because we measure, LHCb measure many new resonances, you measure many resonances. So really to answer question, what are those guys? I don't know what Kafka quote it would be.
Well, as we don't have anything yet, there's no quote to go with it. Your point is well taken. We currently do not have any measurements using the two-photon production, but it is definitely part of our program with spectroscopy.
So it is, just my question is, to be more precise, is this planned?
Yes.
Thank you.
Thank you.
So there was another question here.
Quick question, then.
I think that you said that you're starting to understand the problem with super KB. Of course, this is very interesting because it has a lot of implication for future machines. So are you understanding better this, what is, and how are you going to deal with these sudden losses, beam losses?
So, okay, I am not an accelerator physicist, so I should be careful about what I say. So the good news is there's certain reproducibility now. We know how to induce sudden beam loss inside the accelerator. And that's very much a first step to understanding what is going on. It seems to be related to dust, and we have ideas of how we can mitigate it being such a problem, and that is ongoing during the summer. We have a run starting in October. We will know much, much more after we start again in the autumn. And as I said, a lot of our time is dedicated to machine study and trying to improve the luminosity. So we are very much, the machine people have priority, not physics at the moment. So I can't answer in detail, but let us see. Hopefully there'll be good news come the end of the year.
Okay, thank you. I think we have to move on, so let's thank Jim again.
Okay, and our next speaker is Tracy Berry from Royal Holloway University, and she's going to talk about diversity and equitable opportunities.
Okay, thanks very much. Hello, yes, I'm Dr. Tracy Berry, and I was the EDI contact for Atlas in the last 2 years, and now handed over, and I'm Vice Dean for EDI for my school, which is 5 departments back at Royal Holloway. And it's my great pleasure to be invited here, so thanks very much. And I'm going to give highlights of these, because of course I can't cover everything. So, first of all, I'm talking about diversity. Diversity is being different. And equitable opportunities doesn't mean treating everybody equally. You can actually have to treat people differently to give people the equal opportunities. So, why do we want to talk on diversity and equitable opportunities in a particle physics conference? Some people will think everything's fine, it's nothing to do with me, I'm having a great time. In contrast, there's other people sitting in the audience thinking, there are so many barriers, this is so hard for me, we need to improve things. And there's some people sitting in the middle thinking, everything's fine for me, but I do see barriers for others. So, whether you sit which side of the barrier you sit may depend on your characteristics. Either you're in the in-group, so you belong, or you're in the out-group when you don't belong. And that could depend on your different sort of nationality, gender, language, race. So your journey to this conference may be very different. How you've got here by potentially invited to a talk or to give a poster, that's required a selection process. You've also had to register, so you've had approval by someone, unless you're the approver yourself. You've also had to travel here, so that requires having the correct passport or visa. You've had to transport here, so you've had different funds. And have also, to be able to leave, you may have had to arrange caring responsibilities to even to leave your home. So everyone's experience getting here has been very, very different. The question is, it could have been harder or easier for you at each of these different levels. And what we want to do is make it easy for everyone. So for example, to be registered for this conference, To get an invitation, it may depend on your career stage, nationality, gender. You may have had to go through a speakers committee, or you may be in a small collaboration where you can just put your hand up and say, I'd like to go. To register, you may be biased in the approval process. You may have to go through those. To travel, it depends on your nationality or passport or your health or mobility. The funds, you may have your own funds, that's fine, or you may have to ask approval. And again, home arrangements depend on your gender, age, or ethnicity, whether you can leave people at home or we've got to sort things out before you come. So each of us has had a different step, and that's just to get to this conference. And it could have been easier or harder for each of us. Also, even just to get before that, coming to this conference, we had different opportunities. How did you get to that position? How did you get your PhD position? How did you choose your undergraduate in the first place? Did someone say, this is a good place, or did you have to search through everything yourself? Did your family support you in your career choices, or did you have to find it all yourself? And even when did you hear of particle physics? Did someone introduce you at primary school? Did you only hear about it in your last year at undergrad? So everyone has had very different steps to get here. And your career path can either be hard or easy. You can either be taking a self-determined, lonely path, which could be direct and great, or it could be very lonely or going around all the tracks, taking a strange path that you don't know about because you haven't been told the correct ways to go. So it can be very different for each person. And here's an example, then. This is the leaky pipeline that typically is talk about women, but it actually applies to most minorities. So women are less likely to be employed as graduates, as postdocs in male PI's labs, which is actually 70% of the labs, so it's quite significant. If they then try to get new jobs, they're half as likely to get excellent letters of recommendation, so that's another step. Then when they apply for startup funds, they're going to get paid less. They're 10% or 20% less likely to become an independent PI. Women typically submit fewer grants and then don't have as many renewals as males. And also then, when people have their females put their authors through, they're less likely to have their manuscripts accepted by an all-male panel. Now, of course, that we can address by having not all male panels. So what can seem as a walk in the path and you can go along, have your nice friendly chats, for some people can actually be like walking through mud, and some people have a much harder time getting the same place as others. And so as people drop off, we're actually wasting a lot of talent. And this doesn't apply for women, it's lots of different underrepresented groups. So traditionally, in diversity in physics, we've concentrated on gender, and that's, as you can see, why pictorially you can see, it's obvious, you can see which gender people are traditionally. So here we can see back in 1927, there was one female out of 27 males. I'd just like to point out that that one female got 2 Nobel Prizes in 2 different subjects when none of the other males did. Now you can see we've got a very different situation, and we're concentrating now on more characteristics of being different. Beyond gender, we're looking at all the other things as well. So race, ethnicity, sexual orientation, gender identity, disability, neurodiversity, and age. So now I've introduced the problem, what are we doing about it? So I'm going to discuss now in 2 sections what we're doing about diversity and what we're doing about equitable opportunities. So typically in labs, they're set up like this. There's the research lab, and they have a diversity section. And then there's overall networks, diversity, disability networks, LGBT networks, or women's networks. Then you have the collaboration management, who can make it easier or harder for different groups. And then so typically every lab has, or collaboration has its own diversity offices, and also early career groups. And I'll highlight some of the things that these are doing. And then at the bottom, but most importantly, there's you. The diversity offices have particular mandates in how they're supposed to address things, and the early career groups often have mandates and also making up their own initiatives to support people as they see fit. And as we heard in the session later on, the diversity groups are ensuring they themselves have diverse people. So just to highlight some of the things we discussed in the parallel sessions, they sort of split into talks by collaboration overview talks, and then talks by topic. And also what was really great was on the first night, Friday, there was the first EDI and sustainability discussion where lots of people could get together and involved. So I'd just like to highlight this is really valuable. So please do go along to these sessions. It's really good to hear different points of view rather than just one person talking at you. It's good to get a chance to have your input. And also following this, there's a discussion about outreach, so please attend that. So if you're going to turn off now, this is the one slide takeaway slide from those summary talks. I thought this highlighted it very well, this G-2 summary. The mission of all our collaborations is to do physics, the best physics, unprecedented precision, in this case for the anomalous muon moment, but otherwise the best physics in whatever we're doing. But to do that, as many studies have shown, to do that, the best teams in business and physics require diverse people. and they have a variety of backgrounds, are an asset to solving these complex problems. And to do that, then, we want to make an inclusive and equitable environment where these people can really thrive and work well, to maximize the productivity. So that's the aim of basically all our collaborations. And then to highlight that, then the early career researchers are then really their goal is to make sure that every career scientist that comes into physics has equal opportunities to then achieve, independent of their background or their characteristics. And we had a great talk on the funding bodies, how they're also trying to then address this and make fair funding opportunities. So then, what are they doing distinctly then? So for diversity, first of all, the collaborations are monitoring diversity, many different characteristics, not just gender. They're also then showing this in Atlas Collaboration Board meetings and wider in conferences like this and raising awareness of these issues. And CERN, for example, has a target of 25% females by 2025, and we're on the way to reaching that. So in Atlas, for example, we're about 24% female authors, and similarly in CMS. They're also broadening people's minds. We have to accept that everyone has their own individual background and own lived experience. So you can't be aware of everyone's. So the way you educate yourself is attending culture events, being aware of inclusivity. So that the collaborations hold these diversity days for women in physics, and also LGBT STEM days. The flag was raised this time for the first time at CERN. And there's some really great training going on. So here's Alice doing some inclusivity and cultural diversity training. And they're running workshops to educate people how your unconscious bias that you will have, because you will have had a different growing up or experience to anyone else in life, and how this can bring awareness and cultural awareness, so you can be aware of your characteristics and your biases, and then kind of influence those, and how you can deal better in a cultural collaboration. Also, they're doing training sessions. So traditionally, training, you may have thought, is boring. I hate going to training sessions. But now collaborations are thinking of more fun ways to do training. They're doing theatres, workshops, you can participate and learn and mime and really get involved. And training for everybody and management as well, because it's important that the management learn about these things. Also increasing accessibility. So, for example, CMS are completely changing their style guide for their plots to make it better for people who have colour blindness. And also, they're making interactive books and also leaflets to educate people, because it's okay if you don't know about it, you haven't got colour blindness, we should start to educate ourselves about other people's issues. Okay, so that's, now we're embracing diversity and seeing it is a positive thing. So how are we making it equal for these diverse people? So first of all, outreach. If you never heard of particle physics, you can't do it. So the first step in here, outreach is key. So do attend the session later. Here we are. Outreach is key for diversity and the other way around. So all of the collaborations talked about how they were doing outreach at various different levels, either going out to the people. So here's the fun run that CMS did, going out to people and then bringing them to experiments, or inviting people to come to CERN or to other labs to have a visit or virtual visit. And doing this in many different countries and many different languages to all different age groups. Another one was then another talk by going back into schools. We talk about the pipeline. We want to get enough women in at the start, otherwise the pipeline will go off anyway. So we want to encourage more women and girls in school to study physics. So there's these program events that have been running for over 10 years, a whole workshop, 3.5 days, with various different project activities, meeting role models. And you can see then this is an outcome from the people who attended. Their interest in physics has increased, and they're much more likely to study physics after. So 40% said they would study before, 75% after. So these things can have real effects. Obviously, you're just raising awareness of particle physics. Then there were some great things. If we encourage people to come to our collaborations, we need to sort of treat them and look after them. So here's a good talk by the early career scientist. This is an Atlas example. He said, talk here, Christian said, if you imagine an early career scientist going into a huge collaboration, because let's face it, Atlas and CMS are huge, you can be very lost inside that. Lots of different people. They already have their own networks, and you're stuck there not knowing anyone. So you will probably need help, and that's what the early career forums are there to do, link you all up and sort of help you on the way. And again, mentoring helps. Underrepresented people do better if they've got dedicated mentors. And again, this is followed up by G-2. They want to have rather than seeing the clouds at Fermilab, you want to see a sunny day. So they've got an EDI committee and a G2 early group that are working to sort of ease the transition and make people's paths better. And here's a really good way of showing the whole career from start to finish, how the early career group are running events to help these people on their way. So it starts with induction days, software tutorials, then a year in, you meet up with people, see how you're going, meet and greet to meet other people, And here, then they get mentoring throughout, software skills, and then when you're looking for jobs or other careers, they do job matching, and then have a summer party at the end. So they're doing a whole range of things to help people at every step. LHCb are also concentrating on actually doing an LHC-wide survey on mental health. So it's important, of course, to stay well, so you can do your physics throughout your degree and career. And you can see here, actually, it's quite shocking. So the experience of mental health challenges, 29% of these 400 people who responded from all LHC experiments had daily challenges. And that's approximately equal to those who rarely had challenges. And if you split it between those who have daily and monthly, it's more than those who have yearly or less challenges. So this is really something to take note of. And here, the main stress triggers were work or study, and also down here, environment, which is part of the collaboration can actually contribute to. Then to go beyond collaborations, there was a great talk said by Louis from the research councils, how they're addressing grants and making more equality within the grant system, and also sharing tips. So it was a great talk, so look at his slide for the tips. There's grants available for all different career stages, and he gave us tips on how to be excellence and how excellence is evaluated. So little tips, so explain what you're doing, make it clear, put the basics in there, add some details for the specialists, but don't lose the non-specialists, avoid hype, and as a PI, you don't have to be the best. You just need to be self-prepared and competent and explain that you are going to fulfill what you said you fulfill. And also, don't give up, try again. He also shared some plots. So it was indeed the case that previously females did have a lower success rate than their male counterparts. But more recently, this has become more equal. In fact, females are slightly better in Horizon 2020 calls in this period, and now it's approximately equal, so 12 to 13, 14% now. He also played some great plots by country as well, so have a look at those slides. So then dealing with management, the LZ collaboration, many collaborations already have code of conduct, so they're making environments fair. CMS show these a lot to make sure people are giving people equal opportunities to talk in meetings and everyone's going to have their voice heard. LZ have been doing lots of work now with their community agreement process, and so there's a great talk on how they've proceeded that and how they're going to they've created an ombudsman system, and then how if you have an issue, you can go to them, and then how their overstructure sees, and how they're improving that as they're developing it. So do look at those slides. Also, other collaborations are working on making their collaboration systems more inclusive, so adding pronouns to their databases. Then there was a brilliant talk on Ukraine and their contributions, gave a historical perspective and how important they've been in the past, and also a future outlook. What's notable was iCheck was held in Kiev in 1959 and also 1970. And you've probably seen or heard of many of these famous physicists who were born in Ukraine. Here's Bright, Charpak, and Gamow. And also then to highlight a female here, this lady. So apparently she was discovered these lead tungsten crystals, which are part and used now for the ALICE and CMS detectors. And also scintillators are used presently in the detectors now. And this all comes out of Ukraine. So really have a key part in all of our experiments here. And there's a lot involved in the future that Ukraine's involved in. So have we covered everything? So I've talked a lot about sort of gender and other things. No, there's a lot of invisible dimensions. There's a talk by the CERN lead, Louise, about that and other dimensions. So there's a lot of things you can't see. For example, some people are more than one nationality. So when you say, what are you on a form, it's tricky. People may be the first in the family to go to university, and a lot in the session we had some questionnaires. These are not from that one, but some questions are. A lot of people are the first university, so they won't have had tips from their parents. They have to go and find another network to get those tips that other people may have had. Some people are financially supporting others, so rather than they're spending their money on going out with their friends or making networking, they have to then give their money to their parents to support them. Some people are caring for others, so have to go home immediately to look after people. Some people are neurodivergent or are caring for others who are neurodivergent. So one example was it taking someone a long time to get their children out of the house because they had to put their shoes on. It was taking a long time. So there's a lot of things that people can have had a lot of issues before they even get to work. Another thing is the two-body issue. If people are traveling all the time to be with a partner, they can't have the same opportunities to network at work as others. So these are things that you can't see by looking at someone, but people are dealing with in the background. So then my tips on the final slide is, what can you do? So my best advice are these. So there's 5 tips plus a few extra if you're in a management role. Support everyone in your career and be considerate. So that's be considerate. People who've got to work may have had challenges on the way. Mentor others if you have the opportunity. Be an ally to those treated unfairly. Call out bad behavior if you see it. Don't let other people have to defend themselves. You stand up. And anyone could do this. Don't assume that your lived experience is the same as everyone others. Someone sitting next to you now will have had a very different path to get to where you are today. Learn about others, so equip yourself with others' experience. Attend training courses, and then if you're in charge of others, try to make a positive, fair environment, remembering that you may not have to treat people equally to give them equal opportunities. Allocate resources, which are money, time, PhD students, talks, workload shifts fairly. And some tips, which are very taught by Victoria Martin on physics departments. Have summer students to help analyse your EDI work. Make a team so you're not doing everything yourself, because lots of people can bring to it. And you can have EDI seminars to help spreading the word back at your institute. So finally, don't be scared of EDI. Many people just think, oh no, it's nothing to do with me. Do your best, and everyone creates a positive or negative culture. So be someone to make a positive culture. So thanks very much.
Okay, thank you, Tracy, for this. Sounds like it was a really interesting session. In particular, thanks for the tips at the end. Questions or comments?
Yeah, hi, I have one comment. Yeah, very nice talk. Just, let's say, this is just my personal, how I perceive the situation personally. I saw that essentially the point where people leave particle physics is especially when they start to have caring responsibilities. Mm-hmm. And so anecdotally, it seems to me we are not supporting these young people with kids sufficiently, also people who are caring for elderly people. We are not supporting them sufficiently to keep them in particle physics. Can we do more? Are there plans to do more?
Yeah, exactly. I mean, I think that's a good point, and I think that was actually made by Victoria Martin in her talk. So it was Edinburgh. They've actually made, as part of their sort of Juno process, they're trying to make more grants available for people with career children. One suggestion was that you bring your granny along to conferences to look after childcare, so you can come together. Also having funds to support. So I think there are things people can do, more grants. But I agree, and particularly I think, as you said, it's not just the childcare; it's caring for elderly. I think we need to have more grants and more availability, more things people apply for to help that.
Okay, thank you. There is another.
I guess you put it. It just seems to me that all what you said was quite relevant and very good, but it seems to me that you were missing perhaps an important direction that seems to have become necessary recently, certainly in my country, in certain states, and that is that there needs to be a political component to these discussions, because some of my states, you can't even say EDI in a university environment. And therefore, I think if you just go on and pretend that EDI is a valid political concept in these particular states in America, it's too naive. I think you have to bring that also into this discussion.
Exactly, and I think that point came up really interestingly at the diversity and sustainability discussion, how much we can do as physicists and how much then politics and things influence it and where our stage is. So I agree, it needs to be part of a bigger discussion, and we can't just act as an island. We are part of a bigger world, so I agree it's something we need to address, and maybe sort of more management and people higher level as well. Yeah, thanks.
Okay. Yeah, I'm in the middle here. Hi. One question, so there's maybe one conflicting other movement, let's say, in society, which is minimizing our carbon footprint in the world. And this, for instance, in many universities, we're being discouraged from international travel, essentially, which can have an effect of making the world smaller and less diverse by doing this. I mean, of course, there's things like remote conferences. There's ways to go beyond this, but of course, I think we all like to be here in person and do this. And I think, of course, this conference is very good at moving, location to location and things. But I wonder, how do we bridge these two movements, one that wants to make us, let's say, geographically centered, and one that engages a larger community in the world to do particle physics.
Yeah, exactly. I mean, we discussed that in the discussion session together with the EDI and sustainability, and we didn't come up with the answers, but do join the forum. I think it's still open if you want to join the forum to have some discussion out of that. Yeah, I mean, we completely agree. And I mean, one thing that came out of it was, again, funding to come to conferences. People can have, some funding bodies have, you can travel sustainably, it may cost more, take more time, but funding bodies will cover that extra cost. Again, it goes back to what your university approval system is, so then it goes to politics, so it's all one big thing we need to discuss together, how we want to go forward. So I agree, there's lots more. It's a complicated thing that we need to have all dimensions involved.
Okay. Yeah, I just have a question which maybe complements that one, which is the fact that as we are talking about, for example, we have funding for Amazon, for example, right? So rich countries like Norway and so on give money to Brazil. I'm Brazilian, so I'm speaking about that, to help that Brazilian people can take care of forests. In the same way, don't we think that maybe if you just look at the ICHAP conference or whatever conferences for high energy physics, they are all either United States or Eurocentric. They are built there, right? So shouldn't there be some kind of funding to actually try to really bring this conference to other continents, to India, to Africa, which don't have almost physics collaborators, which I find that a nightmare. This is one question. Yeah. And if I can just comment about the women in science, I do have an impression also, again, looking at my country, the research ministry, whatever is related, it's usually, okay, you can get the best one, which is very equal opportunities and so on for women and for men, that's great. However, if the issue doesn't feed back to the education ministry, the work done here, and I saw many talks in the diversity committee there, this is great work, but I think it's too late. So we have to start much earlier. I lost my daughter, which is very intelligent, for example, and she's probably not going to go to science even though I have all my effort. Yeah. The societal pressure is too big for that, I think.
Exactly. I mean, I think that's where the outreach was key comes into it. And again, go to the session in a minute. Yeah, I agree. We need to change perceptions of it. I mean, it is very different in different countries as well. So perception of physics changes across the countries. If you go to the International Women's Physics Conference, it's very stark there, the proportion of females in different countries that do it. But I agree we need to change societal things. And on the conference venue, again, that was discussed at the session. And again, yes, we do need to share where the conferences are. But again, be aware of, there's lots of things that go into factoring where the conference should be. But I agree in principle.
Okay, I hate to stop this discussion, but since there is a lunch discussion to go into more details, I suggest people go to that also. I also know that the next ICHAP is in Brazil, which is at least further south than Northern Europe, so maybe on the bright side. So thanks to Tracy again and for everybody's engaged in this.
Thank you. Let's welcome Maxime Titov, who will tell us all about technological spin-offs and industrial applications.
Okay. Good morning, good afternoon to everyone, and it's a great pleasure to be here in Prague and to give you a talk following the physics talks, diversity talk related to technology, and perfectly understand that I'm separates you from the lunch break. It's the last talk of the session, but I think it is very important that we keep the technology spin-off industrial session as a part of all of the major HEP conferences, because the key message here, we are coming here because of fundamental physics, but we should keep preserved a virtuous cycle between the loss of physics enable new accelerating detector technology, which turn earns in the practical application, and at the end of the day allows us more investigate the loss of the nature. And I think it's very important that while we're doing fundamental research, we keep very strong the cycle unbroken between the fundamental and applied research. The technology session started for the first time in ICHAP in 2016. And actually, this time, we also had 2 parallel sessions. And I would like to thank to all of the speakers and also to the session conveners for the excellent presentations. I would not go through all of the presentations. We have a really very, very broad scope of different topics addressed, such as waste management, also using muon tomography. Several examples were discussing about the medical imaging from the polarized targets at CERN, and also cryogenics, azumidide, full-body PET scanners. We also have presentations for the picosecond timing and fast timing, which becomes very important in many high-energy physics applications and beyond. And last but not least, we also discussed a little bit scintillation technology, glass crystals, but also the future accelerator facility, like, for example, LARA. So there was a lot of the presentation, but since it is impossible to go and make an overview, concise overview of the technology applications beyond HEP, I decided to select a few key examples of my preference. Apologies if you have different ones, and actually try to guide you through the developments of starting from few examples, detector technology, going to accelerator technologies, to European Union initiatives, and some other. So one of the examples which we all know and which is very, very important and actually shows the importance of connection between HEP domain and applied domain is the MEDIPIX TimePIX technology. The collaboration which started many years ago, which has a lot of the application in HEP, but also being introduced in the space missions, for the clinical trial, for the schools. And we know that the new TimePIX for assembly technology actually works. And the major difference with respect to the, for example, TimePIX 3 is the time for chips fully bootable. So basically, you can put chips with respect to each other. And there is a lot of the other things which is ongoing. And I think the TimePIX 3 is really opening new possibilities with the single layer tracking and hadron therapy. And TimePIX 4 will allow you to cover the seamless way large areas. While the MEDIPIX 3 on 4 chips allows you for some more spectroscopic X-ray imaging in medicine. But what I would like to emphasize is the importance of the MEDIPIX collaboration model, because it can be more difficult to manage, but this is, for example, how you build a community which afterwards can do for the HEP application and beyond. And actually, the point of the newly DRD collaboration at CERN can also help us not only to develop the strategic R&D funding for the future project, but also actually advance the technology transfer and actual application beyond the HEP. So the building the collaboration environment and detector technology is very important for the community in general. Another example which I wanted to select from the detector point of view is the SAPM-based readout. I mean, 20 years ago, when it was presented for the first time, it was certainly a very promising technology, but we didn't know how far we can advance and what would be the time scale of this advancement. The first large application of the SAPM technology took place thanks to the development of the Kali scalarimetry for the linear collider. And later on, now, this becomes a platform for the PET imaging using SAPM. The multimodality approach, such as the development time-of-flight PET systems, it required more and more in the clinical practice. And CPM today starts to represent the future of the nuclear medicine, progressively becoming the photodetector of choice, of course, being slowed down by the high associated cost, but there are many developments. And I will show that this is not only single development, because we have started to use it intensively also in particle physics and in some other application. Moving to the importance of having industry and sustainability session, I would like to point out that at the Linear Collider workshops, the industry session has become an integral part since 2016. Every year we have an industry session. And what was, first it was focused on the ILC and click technologies, also on the free electron lasers using SRF and click technology using X-band. Now it includes C-Cube. So it is not whenever limited to high energy physics application. But what was a change of paradigm is the introduction of joint industry sustainability session. Because sustainability becomes a very important part, not only for our community, but with our future interactions with the funding agencies and more. If we go for the click technology, the X-band technology actually represents many benefits. It can be used in the compact Linux. And actually, now many or most of the developments are driven of the click collaborator for their local application. Here you can see a non-exhaustive list of different applications of X-band technology. And actually today, thanks to these real application points, we have a much stringent industrial base and strong increase in the research experience with the X-band technology and associated components. You now can find the compact Linux for the research, medical, and industrial applications, which provide a widespread adoption benefits for the original click research and society and large. such as the deep electron flash therapy, such as versatile ultra-compact advanced neutron generator, such as research industrial smart ride systems, and also for the future developments, such as acceleration with the plasma, which is being driven by the Eupraxia consortium. So I think the key elements when we discuss about the past, present, and future of accelerated technology, in addition to the primary application, building new high-energy colliders, we need to promote industrial base and application of advanced accelerated technologies as a part of the R&D strategy, which basically innovate through the application. And shows an example of CLIQ shows that the compact and robust accelerator with different parameters, design, and RF solutions has been developed. We have to really focus on the low-cost and energy-efficient accelerated technology as a part of the sustainability strategy. It is very important to maintain and strengthen industrial base capabilities because it allows actually to train and educate a new generation of accelerator physicists. And if you consider the whole landscape of the future projects which we might envisage, basically we need to increase the base of the accelerator physicists in our domain. And last but not least, it is also important to use the future accelerator platforms in a way that it can be synergetic between high-energy physics application, for example, like HAF, and also applications like Eupraxia and LARA proposals. Now, I would like to say a few words about the TIP conference, which took place the last time, and there was it's featured a dedicated session to present and discuss measures to support innovation and technology transfer. And we had a lot of the presentations, starting from the KT offices of different labs, from the European Commission, and also somehow discussion about the future. And this was the first time TIP conference hosted such a dedicated session, and we hope that it would be continued in the future. I think one of the key messages which we should take is that co-development with industry is now must follow the European call. You would not win European Union proposal in case you would not have in industry partners. And actually, if you discuss, for example, you have a couple of the major proposals in our HEP domain, like AIDA, Innova, IFAST, LEAPS, Eurolabs, you have more than 100 industrial partners involved into these points. But of course, we still need to work in order to better understand. We need to mind the gap in language, clock, speed, and culture, which sometimes create a challenge for the co-development of industry. We need to understand better to each other how to work to mitigation strategy and align on sensitive and expectation. In particular, we also need to be proactive to discuss the things with industry. In particular, AIDA, Nova, IFAST, LEAPS, and NOV have teamed up for several events involving industrial partner. And Common Boost at the very large Big Science Forum in Trieste will actually include a common boost from the European Union project, which feature. Now coming to some of the proposals and actually events which were generated within our domains. And one of them is, of course, EUAttract proposal, which was organized with the two phases, with the first stage with a very moderate funding and approximately a few hundred proposals being selected, and the second stage, actually, to mature the proposal, upscaling demonstration, somehow being ready to try to involve the private investment. Of course, if you go from the phase 1 to the end of the phase 2, your combined success rate was not big, only a few %. But I think one of the few key facts which is very important, so basically, even at the low technology level, at the basic level, out of this proposal, 18% of funded proposal got private investments. 30% of the projects got additional national funding, and 34% of the project intend to proceed towards industrialization. So actually, there is an interaction within this call between the industry and our community. Another very important point which was emphasized to us is the European Innovation Council. The total Horizon Europe projects is for 7 years and with a total budget of $100 billion. But there is a place for the questions of the innovation of Europe, and this is where European Innovation Council, which provides you several incentives to apply. There is a support for the innovation with breakthrough in market creating potential. There is a European Institute of Innovation and Technologies and European Innovation Ecosystem. So basically, there are different paths which actually one can go. And as an example of one of the projects which actually was widely reported at this conference, I would like to give you an example of the Antimatter OTEC Innovation Project, which actually is fully funded by the AAC and UK Research and Innovation Council. And the basic idea of this proposal is actually use a reactor and develop both the novel nuclear industry instrumentation, basically using antineutrinos as a direct probe and non-intrusive probe into the functioning of the industrial nuclear reactor. So you basically use a scintillation light, wave shifting fibers, and again, SAPM to develop, to measure the fluxes of antineutrino, which can be very important for the industry and for the IAEA, for example, to check inside the reactor the amount of plutonium with the antineutrinos. And even if the reactor is off, like for example Fukushima, you can still see what is going on inside. And again, it is very important that the SAPM technology in this case has been developed also. So how do we measure innovation in Europe? It's actually a very good slide which was prepared by Massimo Caccio at the summary of the TIP conference. We all know about the invention, which is the process which is coming up with a truly novel idea. And inventions can be considered as stage 1 innovations. And actually, this is what liked by the Ministry of Science. The innovation is a process of using ideas to offer new products and services. And actually, European Innovation Scoreboard, for the third time, published a report last year, which basically distinguishes before 4 main types of innovations for the framework condition, investments, innovation activities, impacts, and basically then try to summarize all these points. And probably the key element, and most of the analysis in innovation economies focus on inventions. But is it really what is really matters? Is there possibly a hype of this mechanism and financial framework which goes with it? So basically on this slide, you can see an average innovation level in Europe, 100%, which is actually increased by 8% with respect to 2016. This is 16, this is 2023 numbers. And actually, this shows you the range of the countries. And actually minds the fact that Switzerland is the most innovative country in Europe beyond the European Union numbers, thanks to the highest performance in education-related indicators, scientific publication, and environment-related indicators. And actually, Czechia is one of the few countries which performance increased by 20% if you look from 2016 to 2023. So the message here, the things is done very well. And of course, this is some of the things which needs to be taken into account when you discuss. We have many presentations. I would like just to highlight that we have a lot of the academy technology industry connection in Czech Republic. There is a number of companies who is being presented here. Advacam company who is using the Timepeaks chip, and actually extreme light infrastructure, which can be considered as a second source for Europraxia project. Last but not least, the sustainability assessment of the future research infrastructure becomes last. The funding landscape are changing rapidly in Europe and beyond, which will require addressing global warming potential in the future large-scale infrastructure. And the life-cycle assessment for the planning of more sustainable accelerators now becomes a must requirement. It doesn't mean that we need to stop making research, but we have to be responsible and address potential points and try to minimize it. And one of the key elements that this has to be done in a close collaboration with the industry. And this is my last slide. The decarbonization of the large-scale infrastructure is very important. But before we really go to this, it's really very important to set a scope of any assessment. The different accelerator project can be a different level of maturity. One would need to understand in each area what are the largest sources, what to focus, not to focus. This is a part of the scope definition. Start to look at mitigation strategy. develop the tools for the life cycle analysis what we discussed. And it was discussed in details at the sustainability session at this workshop. Last but not least, what was mentioned to us by industry, that one of the elements of prioritizing nature-based intervention within and without research infrastructure, integration as a local environment as a part of the asset measurements. And now I'm come to my summary and outlook. Of course, it is not possible to be comprehensive in 15 minutes, but I think technology transfer is crucial for us to maximize the technological knowledge and return to society. Everybody agrees to this. And knowledge transfer and technology is some sort of social responsibility. And it is not transfer, it's an exchange, an opportunity to communicate that we are doing fundamental search, but we keep a close link with society and funding agencies. And researchers together with industry and policymakers must work closely together to accomplish this goal. Thank you.
Thank you, Maxime. We have time for a few questions from the audience. There is one here.
Maxime, thank you for a very nice presentation. So could you comment on two other areas, such as computing and software, and how in these areas high-energy physics could do probably better in terms of cooperation with industry in the world? Thank you.
Well, it is a very broad question. I think one of the points I would limit it to the sustainability elements, because of course we discuss in a lot, but I think our examples in terms of the sustainability, we somehow can be developed and discussed, in particular with larger players, with the cloud computing, etc. I think in this front, we are doing quite well in terms of the address. And again, what I would like to emphasize, and thanks for asking, the key element of the sustainability and the technology transfer, in particular sustainability, of course, we have to be responsible, but in no way our sustainability help should be a showstoppers for the future accelerator facility. So we need to show that we are doing in a way which is reportable to European Union and other authorities, but from the other point of view, of course, any big large infrastructure comes with this, and computing is an integral part of these points.
Any other questions?
Everybody hungry?
Yeah, actually I have one before lunch, Maxime. You didn't talk at all about technology infrastructure, which is something that European Union is working on at the moment that might actually have something to say about innovation and the link between academia and industry. Do you want to comment on that, or?
Well, yes, Frank, you're right. I think it is also very important. I think I was trying to put it more like in a scope. I wouldn't say what are the, how we proceed in this direction, but I would consider that, I mean, for us, it is very important that we try through the infrastructure and help to keep a close link and try to develop together with the applied research, between HEP and applied research. And actually the infrastructure which is used can be used for the common of the both. And I think this is a key message which we would like to do.
Okay, thank you. Any last minute questions before we close the session? I don't see any. Thank you all. Don't move too fast. We have, and first, yeah, thank all the speakers of the session first. And we have a few words from the organizers.
Thank you. I want to give you two announcements regarding the special events that are coming up. The first one is that we are going to have a lively discussion now about how to have an outreach activities improved. This will be happening in Terrace 2A. And for all those that want to actively participate, we have prepared sandwiches there, so you don't have to look for lunch, just go directly to Terrace A after we break here. And then the second announcement is about special discussions with lab directors. So the first one is coming up tonight at 7 o'clock. This will be a discussion on future particle physics and research infrastructures. It will be a limited discussion seen from the Czech perspectives. this event goes in parallel with the iChat party. So all those that booked the iChat party, do not worry to miss anything, because tomorrow there is going to be the main discussion with the lab directors during the plenary sessions in this hall. So you are, of course, welcome to join those. And this is it. Enjoy your lunch, and we reconvene at 2:30.